This is the 5th video in the series on the theory of gravity, and I'm going to talk about energy and gravity. And you may remember that in previous videos I've expressed concern over the use of two bodies of mass without actually including the mass of both of them in the equations, such as the equation for kinetic energy half mv squared. Includes the mass of only one body, and yet energy, in potential energy, certainly requires the mass of two bodies. So I have for some time now been using a different equation for energy, although it is related to this equation and can be converted to this equation. But this uses what I call the energy equivalent length, or separation. You take two bodies, say the Earth and the Moon. They are separated in space, as we know, but that doesn't include any value for their different velocities, with the Moon particularly going around the Earth, and prior to that, when it was leaving the Earth, it was leaving at high velocity. And there's no allowance in the separation in space for the energy due to kinetic energy. But if you take the maximum value of potential energy when, for example, when the Moon left the Earth, it travelled at just under 25,000 miles an hour. Had a tangent initially, but eventually more or less straight away from the Earth, and reached a height where it stopped. And at that point there's no kinetic energy, so the energy, I call that R0, which is the initial energy when it's reached its maximum height. That represents all of the energy. And so the separation between two bodies, which is partly in space and partly in another dimension that I'll get to in a moment, that represents kinetic energy. The total energy can be represented by that length. Never mind the scale, it's non-linear, that represents energy, but that length, the total separation, which as it turns out is about not quite 1.5 times the distance that it is now. But we can separate that separation into two parts. One that represents the potential energy, which is the separation in space. So this is the separation in space between the Earth and the Moon. And this is the separation in a dimension that is perpendicular to space, and which represents the kinetic energy at any moment. So here, for example, nearly half the energy is kinetic and the rest is potential. This would be when the Moon was on its way to its present location. I call that the X dimension. And I have equations that represent those different energies, and which I will now give you. So if we take the total energy as equal to the product of the masses, as Newton did in his equation, for force, mass times the universal gravity constant G divided by R squared. That was the equation that he used. And so his energy is that equation integrated for distance, and that gives you an equation that includes the product of the masses. So this represents the magnification of the energy as a result of the masses. Energy between two bodies depends on the number of mass relationships, which is this number here. And I multiply that by, yes, the distance squared. Now, that will sound a little strange to anyone familiar with energy and potential energy, because the force of gravity, according to Newton, decreases inversely proportional to the distance. And the further you go out, the less rapidly the energy increases. But as I pointed out again in earlier videos, that's a little bit misleading, because the universal gravity constant G actually has the cube of the separation in space, and which actually more than covers this. And this, as you'll see later, or see right now, is very similar to Newton's equation. But I'm leaving it like that, and for now, that's the total energy. The potential energy due to space is simply this distance here, and since they're squared, you add them as vectors, and then this is mx squared. This is the kinetic energy, this is the potential energy, this is the total energy. Now I'll show you how it can be converted into the usual dimensions for energy right away. If we take any of those, they're very similar equations. That's one thing I like about them, is that they look similar. If you take a mass and a mass times average of a distance squared, and you multiply it by a function f, which actually replaces g. G, universal gravity constant, has the dimensions of length squared divided by mass times the square of time. And this is the time period of the system. I'm going to use f as simply equal to 1 over the mass times the time squared, because I've already got the distance in there. So in this now it becomes mmr squared over mt squared, and that has the dimensions of mass times velocity squared. There's no 2 in there, no half in there. That I'll leave for the moment. But that shows you that this can represent and certainly be proportional to the energy, even if there is this factor of 2 difference. And that's true of both the potential and the kinetic energy. I don't usually use notes, but in this case I am, because I want to make sure that I cover all the details. Now, if you now take the Earth and we draw a circle around it, if the radius of that circle is equal to r0, which is the total separation and represents the total energy, then if we're going to conserve the energy between 2 bodies that are in free fall, free to move, if the energy of the moon, which at the moment is orbiting the Earth at pretty much the same distance, but even when it was on its way up from the Earth, its energy then was mostly kinetic, and this energy, the total energy, was constant. So I'm saying that there is an imaginary, if you like, an imaginary circle or ring around the Earth, which actually is a sphere because of the 3 dimensions. So this actually is a sphere. If that represents a constant energy, then the moon is on the surface of this imaginary circle at all times, and it has been since it left the Earth. Even when it was on its way up, it was out there because of its kinetic energy, and now it's there because of its combination of kinetic and potential energy. Now, the dimensions of this are quite large in number, because there are in fact 9 dimensions of separation. And although it's a sphere like this, we can't imagine anything larger than 3 dimensions, so we take 3 dimensions. But you can have 9 dimensions in a sphere such as this. And the way you do that is you say, let's this one be the x dimension, that this one, or one of the x dimensions, and this is one of the space dimensions. There are 3 space dimensions, 3 x dimensions, and we won't go into it now, but there's also the time separation, which is related to increase in mass and time dilation. But for the moment we can only show 2 dimensions on the board and 3 here. This has 2 dimensions of space at least. Now if you take x here now, then if you take these 2 coordinates here, this one is the height in space above the Earth. This is the separation in the x dimension that represents the velocity of the moon. And this is the triangle that I showed you before. So we can say therefore that when the moon left the Earth, the distance in space, was very small. The moon was here. And it was leaving the Earth at about just under 25,000 miles an hour, traveling upwards. And as it went up, so its kinetic energy decreased and the potential energy increased. And from this we can get the relationship between x and velocity, and the x is equal to the velocity in that particular space dimension that it represents. In this case, one of the space dimensions. You only need one when the Earth and the moon were separating in a straight line. And we need to put it here. I use a Greek letter tau, which represents the frequency, or in this case the inverse of that, the period of the system. And this then gives you the v squared, which is this, times this squared, in the equation that I showed you earlier, that the kinetic energy was equal to mv squared t squared. Well, I said x. So that's how you represent kinetic energy. Now, as I said, there are more dimensions, and we need to include at least one more, because the moon, as we know now, at this moment, is in a roughly circular orbit. So that we have to show 2 views of the energy shell, one which I've shown you already, which is the x and r, and one with this r dimension, and the other r1 and another space dimension. So that here you see, showing that here, if this is the x dimension going through here, this way, then this would be one of the r dimensions, and this would be another of the r dimensions. So that this would be, the view of this would be like, well, I've done it the wrong way around, showing you both the vertical and the horizontal, if you like, space dimensions. This one shows you the r, this one does. This is the x and the r, and this is 2 space dimensions. And we can show the moon's entire, or rather its 2 fundamental orbits. One when it started here and orbited in a great circle, like this, going straight up. Now, looking at it in space, it would be going up, like down away from the Earth, and then it would have come down and just missed the Earth, and done this for a while, but later its orbit expanded into 2 space dimensions, like this, X dimension now comes out this way, and so we're not seeing the X dimension. But here it's orbiting in a circle, but it's not going round this way. It actually has now a fixed value for X. So here, if it's going round, it will be going round in a smaller circle. This is the moon now, going round in space, because there's no, the kinetic energy that it had in excess is this part here, that now is coming out this way. So this circle is on the surface of the moon like this. It's still on the surface of the moon is on the surface of the Earth's energy sphere, but it's separated in the X dimension. So it's actually here, and when you put that on here, you get it like this. This is the moon now going round like this, and looking at it from the side, it's that. So this X dimension is now constant, and that is the constant, or nearly constant, separation in space. I'm so sorry, I got it wrong. The velocity is constant. The velocity is constant. This is the velocity. The velocity is constant, and the separation in space is constant because it's orbiting like this, in this way. So both the kinetic energy and the potential energy are now constant. And you'll see that the kinetic energy and the potential energy are roughly the same. And this is where my equations for energy, I think, give a more accurate, in my opinion, might give a more accurate measure of the energy than the half mv squared and Newton's equations. So here, this value of x and r are roughly the same, and r is in 2 dimensions. We've got 2 dimensions of space and 1 of the x dimension. That's all you need, only 3 total dimensions to describe the path of the moon right now. So that, I think, is enough for this video. I've reached 15 minutes. I've now got a timer with me, and so I'm going to continue on a later video. Thank you.